Okay, now the other category, if you look on your equation sheet, is this is on the right-hand side. They unpack leptons, and you guys know one of the leptons at least. You know there are 6 types. We have the electron, which you know we're very familiar with, the charge of -1. And then we have an electron neutrino, and so you've actually seen that as well. We just didn't put the little e there. The muon, and so it's kind of nice, you know, the Greek letter mu. So it's the muon and the tau, and they are corresponding neutrinos, the muon neutrino and the tau neutrino. Now, the muon has is actually heavier than the electron. The tau is heavier than the muon. So if you work your way from left to right, you know, you're working, you know, it's heavier. So the tau is heavier than the muon. Muon's heavier than the electron, and they're all a charge of -1. Now it turns out that the neutrinos have a very, very, very small amount of mass. And it's been proved that they have a small amount of mass, but a crazy small amount of mass. And they're very hard to detect. We have billions of them going through us right now because in the sun, and the reactions of the sun, they shoot out and they're passing right through us without being detected because there's no charge, so the electromagnetic force is not interacting, right? And they have a very, very small amount of mass. They just pass straight through. So all leptons interact with the weak nuclear force, and that's important as well. And so, you know, out of all 6 leptons, you know, the top row is the only one that interacts with electromagnetic force because they're the only ones that have charge. Now, all the leptons, just like the quarks, have their antiparticles. So you have an anti-electron, which is a positron, positively charged electron. You have the anti-muon, the anti-tau, as well as the anti-neutrinos, which we've seen before too, right? The anti-neutrinos of each of these. Now, all leptons have a lepton number of 1. Anti-leptons have a lepton number of -1. And we know that all the lepton number must be conserved, just like the barium number. So let's say we had an electron and an anti-electron or positron, same thing there. What would happen, right? So if you think about it in terms of charge, the electron's -1, the anti-electron would be +1. So we bring those together and we get 0 charge, right? With the lepton, we add up the lepton numbers and we get 0. So again, we get annihilation, right? The electron and the anti-electron annihilate, and we're left with energy again. All right, so let's take a look at an interaction with strange number, and let's use this example here with a neutral kaon, and it has a strangeness of +1, and so we can depict that with a K, and then looks like a degree symbol at the top there. And let's look at a lambda particle, and you can draw that out. And let's say that the lambda particle has a strangeness of -1. So let's say that we have a proton and a negative pion, and these 2 particles interact. And if we look at the proton is an up quark, and a down quark. The negative pion is a anti-up quark and a down quark. All right, so and then we have a strangeness of 0 here. And if we look at the these 2 particles, okay. So let's say that afterwards, after these 2 particles interact, the proton and the negative pion, we have the neutral kaon and the lambda particle form. Now, the strangeness after, we add them up, and that equals 0. And so the strangeness before is 0, the strangeness after is 0. And so the strangeness is conserved there. We have the kaon with the down quark and the anti-strange, or the anti, I'm drawing a blank with that, the strange quark, and the up quark, down quark, and the strange quark. And yeah, and so we have those there, and then we can check for conservation of charge and baryon number. So if we look at that, the charge before is with the proton is positive 2/3 plus the positive 2/3 plus the negative 1/3, and then we add this to the negative pion, which is negative 2/3 plus the negative 1/3, and then afterwards we have the neutral kaon with the negative 1/3 plus the negative 1/3, and then we have the lambda particle, positive 2/3 plus the negative 1/3 plus the negative 1/3, and so the charge before is 0, and then the charge after is 0, so that looks good. And then the baryon number, the proton 1/3 plus 1/3 plus 1/3, and then the negative pion is negative 1/3 plus 1/3, and then for the kaon afterwards, the positive 1/3 plus the negative 1/3, and then the lambda particle is 1/3 plus 1/3 plus 1/3. And so one before, one after, and the baryon number is conserved as well. So another important principle when we consider this is the fact that strangeness may not always be conserved. If there's a weak interaction, it is not conserved. But again, the charge, baryon number, and lepton numbers must always be conserved. So let's take a look at this instance here. We have a kaon decaying into a positive pion and a negative pion. So here are the values here for the quarks. We have a down quark and the anti-strange quark for the kaon, up quark and an anti-down quark, plus the anti-up quark and a down quark. And so, yeah, and so in this case here, this would be a good chance to practice this. Why don't you go ahead and practice the charge. Go ahead and get the charges for each of these and see if charge is conserved. And then also the baryon number as well, and then and check that, and then we'll talk about the strangeness as well. But go ahead and get those two, and pause the clip and do that, and then when you're ready to check, you can hit play to continue. All right, so the strangeness, the kaon has a strangeness of +1, and afterwards the strangeness is 0, so the strangeness is not conserved. Therefore, we know that there's a weak interaction that takes place. But again, we can verify the conservation of charge and baryon number here. So we have the down quark, which is negative 1/3, plus the anti-strange, which is positive 1/3, and then we have the up quark, positive 2/3, plus the anti-down quark, negative 1/3. And then we have the negative up quark, or the anti-up quark plus the down quark. And yeah, and so before the charge is 0, afterwards the charge adding up is 0. And then the baryon number as well, we have 1/3 plus negative 1/3. And then we have on the right side 1/3 plus negative 1/3 plus negative 1/3 plus 1/3. And the baryon number is conserved as well. Now, what's interesting in this with the electromagnetic force, classically what we've been talking about, is that the electric fields are pushing off each other. But actually what's happening according to the standard model is that there's an actual exchange. So here's an electron, right? And this electron are both moving, and they interact with each other. They push off each other. This electron takes off this way, right? The other electron takes off this way. And what actually happens is there's an exchange of a photon. So this electron shoots a photon off like this. It hits this electron in conservation of energy or conservation momentum. They both head off, right? It absorbs it. This electron, however, when it shoots this off, it shoots off in this direction, conservation of momentum. And so really, in the electromagnetic force, we're dealing with the exchange of a photon, which should, it's kind of sounds kind of strange, right? So again, the top electron shoots off, or shoots out a photon, and then goes to the bottom right, and then the bottom photon absorbs the photon and goes downwards. Now, Richard Feynman helped, well, he did a lot of things, but one of the neat things that he was able to do was communicate these very, very difficult ideas into ways that normal people like us could understand, right? Just people that aren't experts in particle physics. Now, these diagrams, are a little bit well, they're very helpful. They can get quite complex, and so we're just going to look at the very basics of it to look at that. Now, for the diagrams that you're going to see here, the time is going from left to right, and so you'll see that here.